Lesson 12 is about special right triangles. In 12.1, we're going to learn about 30, 60, 90 triangles. That's one of the special right triangles. And then in 12.2, we're going to do 45, 45, 90, which is the other type of special right triangle. So starting up at the top, missing side lengths of 30, 60, 90 triangles can be found using the following relationships. Let me backtrack a little bit. It's called a 30, 60, 90 triangle because those are the angle measurements inside the triangle. So all of the angles in a triangle would have to add up to 180. So 30 plus 60 plus 90 is 180. It's just one of our special types of right triangles. Okay, so the relationships are, the first one is that the shortest leg of that triangle, which a leg is a non-hypotenuse side, the shortest leg is going to be x. The longer leg, which again is just still a non-hypotenuse side, is going to be x times root 3, or the short leg times root 3. And then the third one is the length of the hypotenuse, which is the longest side of a right triangle, and the side across from the right angle is going to be 2x, which means it's double the short leg. So if we look at the graphic on the right, the short leg is on the far right side of the triangle right here. So that's going to be x. If we take that leg and we multiply it by the square root of 3, that's going to tell us the length of the long leg. And if we take the short leg again and we multiply it by 2, that's going to give us the length of the hypotenuse. So everything is kind of in relation to that short leg, which is given x, as it's kind of little mini formula. And then, yeah, just like I said, the short leg is the shortest side of that 30, 60, 90. The long leg is kind of the middle side. And then the longest side would be the hypotenuse. One thing to keep in mind is that the angle size opens up to the side length. Okay, that sounded weird. What I mean is if the shortest leg is going to be across from the smallest angle, because the smallest angle has the smallest opening. So that 30 is going to open up to the short leg, and 60, the middle angle, is going to open up to the long leg, because that's kind of the middle side overall. The hypotenuse is always the longest. And then the right angle, that's the 90-degree angle, is going to open up to the hypotenuse. Okay, so example 1, the short leg of a 30, 60, 90 triangle is 5. Find the other two sides of the triangle. So the way that I like to approach this is, if I don't have a triangle, I'll draw one, and then I take those little mini formulas for each side and I put them around it. So the shortest side, that's x, the short leg, and that's supposed to be across or opposite of the 30-degree angle. So x would go right here. And then the long leg is supposed to be x root 3, and that's across from the 60. So x root 3. And then the hypotenuse is across from the right angle, and it's the longest side overall. So that's 2x. And then I take the side that I'm given. So for this problem, it says the short leg is 5. So I'm going to take that 5 and set it equal to the formula that goes with the short leg, which is x. So we already know that x equals 5. And this is kind of the best case scenario when we're given the short leg. It's the easiest version of this problem, because now if I know that x equals 5, well, I just have to take that 5 and put it in for both of the other x's to find the other two sides of the triangle. So let's do the longer leg next. I would take that 5 and put it in for x. So the longer leg would end up being 5 root 3. And then for the hypotenuse, I would take that 5 and I would put it in for x there. So it would end up being 2 times 5, so 10. So the short leg is 5. The long leg is 5 root 3. And then the hypotenuse would be 10. Example 2, the long leg of a 30, 60, 90 triangle is 15. Find the other two sides. So I approach this the same exact way. I'm going to take those formulas and kind of write it around my triangle. So the short leg, x, goes across from the 30 degrees. The long leg, x root 3, goes across from the 60 degrees. And then the hypotenuse goes across from the 90 degrees, and that's 2x. So in this case, we're given that the long leg is 15. So I'm going to take that 15 and set it equal to the formula for the long leg. And if you have a problem like this, you can't really get straight from the long leg to the hypotenuse, what you really have to do is treat this like an equation and solve for x, and then you can use that x to find the short leg and the hypotenuse. So I'm going to just kind of take this whole line, and it already is an equation, but I'm going to write it off to the side now. So it'll be x times the square root of 3 equals 15. And then now I need to solve for x, so I would have to divide both sides by the square root of 3. So the square root of 3 divided by the square root of 3, that cancels out, so leave me with just x. And then we can't divide 15 by the square root of 3 because the 15 is not in a radical, but we have to do something it's called rationalize the denominator. And that means to get rid of the radical in the denominator because we're not supposed to have them there. And to do that, you have to multiply numerator and denominator by that radical that's down there. So since we have a square root of 3, we're going to multiply numerator and denominator by root 3. So then what that does is I'm going to scooch this over a little bit so I have a little bit more space. In the numerator, I have just 15 times root 3, so I can just write those side by side. I wouldn't multiply them together inside since the 15 wasn't in the radical. And then when I multiply the square root of 3 times the square root of 3, that would give me the square root of 3 squared. So the square root of 3 squared, if you have something that's squared in a square root, those just cancel each other out. They're like inverses of each other. So root 3 times root 3, anything times itself becomes squared. So it becomes the square root of 3 squared. And then the radical and the exponent cancel each other out. So you would just be left with the regular 3. No more radical because the radical has been canceled out because we multiplied in another one. And then now I want to reduce it. So both 15 and 3, they have a common factor, or I can just go ahead and divide 15 by 3 since that 3 in the denominator is no longer in a radical, so I can do that now. So 15 divided by 3 would be 5, and then the root 3, that would just kind of stay as is. So we would end up with x equals 5 times the square root of 3, and that's going to be the same x as we have over there on the short leg. So we just found the length of the short leg. It would be 5 times the square root of 3. And then now I just have to take that value that we got for the short leg, the 5 root 3, and put it in my 2x to get the hypotenuse. So that would be 2 times 5 root 3, and we would only multiply the 2 and the 5 together because those are the numbers that aren't in the radical. The 3 in the radical would stay the same. So 2 times 5, that would be 10. And then times the square root of 3. So we were given the long leg, that's 15. We found that the short leg is 5 root 3, and the hypotenuse is always double the short leg, so it would be 10 root 3. Okay, example 3, the hypotenuse of a 30, 60, 90 triangle is 1. Find the other two sides of the triangle. So same thing, we have our picture. I'm going to set up our little formula, so it'd be x. For the short leg, x root 3 for the long leg, and then 2x for the hypotenuse. In this case, we're given that the hypotenuse is 1. So we're going to take that 2x and set it equal to 1. Kind of same approach here where we need to solve for x really to be able to find definitely the short leg, but also the long leg as well. So I'm going to take this kind of equation that we just wrote, 2x equals 1, and I'm going to solve that for x. And if you recognize that the hypotenuse is 1 and you know that the hypotenuse is double the short leg, then you can just kind of jump to the short leg is 1/2. But if you'd rather kind of see it written out and solved, that's fine too. So we're trying to solve for x to get the short leg. So I would have to divide both sides by 2 to get x by itself. So 2 divided by 2, that would cancel out, and then I would be left with x equals 1/2. And that's the same exact x as the x on our triangle, so that means that the side length of this one would be 1/2. And then I just need to take that 1/2 that I found for x and put it in there to get that longer leg. So that would be 1/2 times the square root of 3. And I could think of this as like root 3 over 1, and then I could just multiply straight across, and that would become the square root of 3 over 2. So we're given the hypotenuse is 1. We found the short leg is half of that, so it'd be 1/2. And then the long leg is root 3 times the short leg, so it would be root 3 times 1/2, so root 3 over 2. Okay, next, find the trig ratios, which are sine, cosine, and tangent of each acute angle. So this was hopefully something that you learned back in geometry, but if you forgot it, it's not a big deal. We're going to review it here. So there's more than 3. There's like the reciprocals of them, but we're just going to focus on sine, cosine, and tangent. So the formula for finding sine, and sine, cosine, and tangent are like ratios, meaning like they show relationships between the sides of right angles. So, right triangles. So if we have sine, that means it's going to be the opposite leg, which we'll talk about that in a sec, over the hypotenuse. Cosine is going to be the adjacent leg over the hypotenuse. And then tangent is going to be the opposite leg over the adjacent leg. So those are the 3 formulas. You may or may not have learned like kind of that trick to help remembering it. It's like SOHCAHTOA. So it's like SOH, CAH, and then TOA, and that's just kind of like it shortens down the formula. So it's like saying sine is opposite over hypotenuse, like SOH. For cosine, CAH, it means cosine is adjacent over hypotenuse, and for tangent, TOA, it means tangent is opposite over adjacent. So we're going to use like these side lengths that we found in example 3 to find these trig ratios. The first round we're going to be all for like the 30-degree angle. So once we kind of identify what angle we're going to be using for our trig ratios, we have to figure out what is the like opposite and adjacent side. So the hypotenuse is always like that side that's across from the right angle, so that's kind of stagnant. But the like adjacent side is going to be like the angle that or the side that helps create the angle, and the opposite side is opposite of that angle. I think I'm actually going to redraw the triangle, just like one that doesn't have all the scratch work around it. That didn't turn into a triangle. Okay, so if this is my like 30-degree angle in there, this is my 60, this will be my 90. So we figured out the short leg was 1/2. The long leg was root 3 over 2. And then the hypotenuse was 1. So in relation to the like 30-degree angle, the hypotenuse is always the hypotenuse, no matter what. So that's going to be the hypotenuse right there. And then the next one I suggest labeling is going to be the opposite. Usually that's easier to find than the adjacent one. So if you take a like arrow and you draw it like pointing out of your angle, it's going to point at the opposite side. So in this case, that 1/2 is going to be the side that's opposite of the 30-degree angle. But if you change angles, that's going to change. And then the adjacent side is the leg that helps create the angle. So that would be that root 3 over 2. But again, sometimes the adjacent leg is like the hardest one to find. So maybe do hypotenuse and opposite first if you're having a hard time. And then the third one would have to be the adjacent. Okay, so sine, the formula is opposite. So I'm just going to do O over H. So the opposite side was 1/2. If we just look at how we labeled it on the triangle, over the hypotenuse, which was 1. So 1/2 over 1 simplifies just to 1/2 because anything divided by 1 is itself. And then cosine, 30 degrees, cosine is adjacent over hypotenuse. I'm just going to do A over H. So the adjacent side was root 3 over 2, and the hypotenuse was 1. So root 3 over 2 over 1 just simplifies to root 3 over 2. Same thing, if you just divide by 1, it stays the same. And then tangent is opposite over adjacent. So the opposite side, that was 1/2. Over the adjacent side, that was root 3 over 2. And this one we do have to kind of do some simplifying. So remember that fractions are like division. So we can think of this as 1/2 divided by root 3 over 2. And then usually instead of dividing by fractions, we change it to multiply by the reciprocal. So I could change this into 1/2, and then instead of divided by, it'd be times root 3. Nope, I forgot to flip it. Sorry, multiply by the reciprocal. So we're changing the like divide to multiply, and then we would take the reciprocal of that second one. So it would turn into 2 over root 3. And then now when I'm multiplying, I can go ahead and I can cross cancel those 2's because they have a common factor of 2. So they would both become 1's, and then I can multiply straight across and I get 1 over root 3. Sorry, I think this one is the worst in terms of simplifying. And then we have 1 root 3. I'm going to drop that down here. Remember, you can't have a radical in the denominator. I'm sorry. So we have to get rid of it. So to get rid of it, we have to multiply numerator and denominator by that radical. So I would multiply numerator by root 3 and denominator by root 3 as well. So I can multiply straight across. In the numerator, 1 times root 3 would just be root 3. And then in the denominator, this becomes like root 3 times itself, so root 3 squared. And then if you have a like radical, square root, and an exponent of 2, they cancel each other out, so this would just become regular 3. And then now, like finally, that's as simplified as it can get. We can't divide like the 3, square root of 3 by the regular 3, since the regular 3 doesn't have a radical. So sine of 30 would be 1/2. Cosine of 30 would be root 3 over 2. Tangent of 30 would be root 3 over 3. So the thing that's nice about these is these like special right triangles pop up a lot in this unit, and regardless of how big the triangle is or how small, they are all to the same scale if they have the same angle measurements. So you could have a really tiny 30, 60, 90 or a really big 30, 60, 90, and their like trig ratios are always going to simplify the same. So like sine of 30 would always be 1/2, and cosine of 30 would always be root 3 over 2. Okay, so now we're going to do sine, cosine, and tangent of like 60. So if our angles are changing, that means that our opposite and our adjacent sides are going to change as well. The hypotenuse will always be the hypotenuse though. So now we're focusing in on like the 60. So to find my opposite for 60, I'm going to draw an arrow like pointing out of the 60-degree angle. It's going to point at that long leg, root 3 over 2. So that's going to be my opposite side this time. And then the adjacent side is the leg that helps create the angle. So that's going to be the 1/2. So now sine is opposite over hypotenuse, just O over H. So in this case, the opposite side, that was root 3 over 2. Over the hypotenuse, that's still 1. So root 3 over 2 over 1 just simplifies to root 3 over 2. So sine of 60 is root 3 over 2. For cosine of 60, it's adjacent over hypotenuse. Adjacent is 1/2 of the, like adjacent to 60 is 1/2. Over the hypotenuse is 1. 1/2 over 1 simplifies just to 1/2. And then tangent of 60 degrees is, tangent is opposite over adjacent. So the opposite leg is root 3 over 2 in this case. And then the adjacent leg is 1/2. So this one we do have to simplify, but I promise not as bad as tangent of 30. So we're going to do kind of the same thing. Think of it as division because it is division. Root 3 over 2 divided by 1/2. I'm going to change it to multiply by the reciprocal. So it'd be root 3 over 2. And then instead of divided by, it'll be times. And then I'll flip that 1/2 into a 2 over 1. The 2's can cross cancel since they have a common factor of 2. They would both become 1's. And then now I can multiply straight across. So root 3 times 1 is root 3. And then 1 times 1 is just 1 in the denominator, but I don't need to write that. So tangent of 60 would just be the square root of 3. Okay, and then same thing, regardless of how big or how small the triangle is, sine of 60 degrees will always end up being root 3 over 2. Cosine of 60, always 1/2, and so on. Okay, sorry, the Zoom was bugging out a little. So 12.2, this is moving down to second type of special right triangles, which is a 45, 45, 90. So missing side lengths for 45, 45, 90s can be found using the following relationships. And a 45, 45, 90 triangle has two 45-degree angles and one 90. Because it has two of the same size angles, it's going to have two of the same size legs. So the first one is going to be the length of both legs is x, and the length of the hypotenuse is x times root 2. So if you take the length of the leg and you multiply it by the square root of 2, it would give you the hypotenuse. So if you notice, like right here, one leg is x, right here, one leg is x, the hypotenuse is x root 2. Notice they're not labeled as short leg, long leg because they're both the same length. And then the hypotenuse, again, is always across from the right angle. Okay, so example 1, a leg of a 45, 45, 90 triangle is 6. Find the other two sides of the triangle. So notice that like this triangle doesn't have the same orientation as like this one over here. It's important to be able to recognize because not every triangle is going to be organized the same way. However, you see like this has two 45-degree angles. It also has like the two tick marks to show that the side lengths are the same and the right angle. So you'd have to be able to identify, like if it didn't tell you exactly, that this was also 45, 45, 90. Okay, so we're going to treat it the same way. We're going to write the formulas around the outside. So one leg is x, the other leg is also x, and then the hypotenuse is x root 2. So for this one, we're given that the leg or a leg is 6. So I'm going to say x equals 6. That's going to be the same thing as this x over here. And that 6 for x can go in right there to give us the hypotenuse as well. So this would be 6 times root 2. And then I would just leave it as is like that. So both legs are 6, and then the hypotenuse is 6 root 2. Example 2, the hypotenuse of a 45, 45, 90 is the square root of 32. Find the other two sides of the triangle. So in this case, I'm going to go ahead and fill in the formulas really quick. So x, and then x root 2. So they give us the hypotenuse is the square root of 32. So I'm going to take that square root of 32 and set that equal to x. And then I'm just going to take that equation pretty much that we just wrote and kind of write it off to the side so we have a little bit more space to work on it. So it'll be x root 2 equals the square root of 32. And there's actually a couple ways to do this. One option, we could divide by the square root of 2. Actually, I think I'm going to do that way. There's a couple different ways. You can simplify the radical and then divide and you'll end up with your answer. Or if I like recognize, and most of the time, like if you see a number being multiplied by x, you're going to divide both sides by x, or divide both sides by that number. So I'm going to divide both sides by 2. Or the square root of 2, sorry. So it's x times the square root of 2. I'm going to divide both sides by the square root of 2 to cancel it out. And then I will have x equals, and if you're dividing and if both numbers are in the radical, or multiplying for that matter, if both numbers are inside the radical, it's okay to multiply or divide them. It's like as long as they both have that square root. So like the square root of 32 divided by the square root of 2, you could do 32 divided by 2, and that would be the square root of 16. And then the square root of 16 is 4. So we would end up with x equals 4, and then that's going to be the same as this x. So this side, why did I write a 5? This side is 4. And that means that the other leg is also 4. So the hypotenuse is the square root of 32. Both legs are 4. One of the other methods to kind of find x is in the workbook too. So if you want to check out the 12.2 workbook, you'll see another example of it. Okay, so example 3. The hypotenuse of a 45, 45, 90 triangle is 1. Find the other two sides. So I'm going to label my sides x, and then x root 2. And then again, they tell us the hypotenuse. They say the hypotenuse is 1. So I'm going to take that 1 and set it equal to the formula that goes with the hypotenuse, which is that x root 2. I'm going to take that like equation that we just created and write it over here to figure out what x is. So x root 2 equals 1. I need to divide both sides by root 2 to get x by itself. Root 2 divided by root 2 cancels out. And then I have another like radical in the denominator that I have to get rid of. So this time it's a root 2. So I'm going to multiply numerator and denominator by root 2. And then I can multiply straight across. 1 times root 2 in the numerator would be root 2. And then in the denominator, it becomes like the square root of 2 squared because you're multiplying something by itself. And then the radical and the exponent cancel each other out, so it would just be regular 2. And then 1, 2 is in a radical, 1, 2 is not, so we would leave it as is, and that's as simplified as we can go. So we would have x equals the square root of 2 over 2. And that is like the same thing as this x, so x equals the square root of 2 over 2, and then the same thing as this x over here. So both legs would be root 2 over 2. Okay, next, and then this is the last section of the notes, find the trig ratios of the 45-degree angles. So it's kind of nice, like up here, we had to find sine, cosine, tangent of 30, and then we had to find sine, cosine, tangent of 60. We have to do both the acute angles, which means less than 90. That'll always be the case, is finding like trig ratios of acute angles. In this case, like the two acute angles are both 45, so we don't have to do 2 separate sets. We just get to do 1 set, and it would count for both. So I'm going to go ahead and add this triangle up here down below just so we can reference it for like opposite and adjacent sides. So sorry it's so small. So again, find the trig ratios, sine, cosine, tangent of the 45-degree angles. So now, because like we have 2 of the same angles, it like is a little bit more forgiving as far as what we pick for like opposite and adjacent. So just focus in on one 45-degree angle. We know that like the hypotenuse is always that longest side, is the side across from the right angle. If I pick that 45 that's in like that upper left corner, the opposite side is going to be like root 2 over 2. That's this side right there. So that's my opposite. Again, this was my hypotenuse. And then the adjacent side is the side that helps create it. So that root 2 over 2. But again, like opposite and adjacent here are the same like thing. So no matter what angle you pick, it's going to have the same outcome. Okay, so sine is opposite over hypotenuse. So the opposite side was root 2 over 2, and then the hypotenuse was 1. So root 2 over 1 simplifies to just root 2 over 2. Cosine is adjacent over hypotenuse. The adjacent side was also root 2 over 2 over 1, the hypotenuse, and then again root 2 over 2 simplifies to just 1. Or sorry, root 2 over 1 simplifies just to root 2 over 2. I don't know how I said it the first time, but it was definitely not correct. So root 2 over 1 simplifies just to root 2 over 2. So you're getting the same thing for like sine of 45 and cosine of 45, because again, like the opposite and adjacent sides are the same because the 2 legs are the same. And then for tangent of 45, tangent is opposite over adjacent. So the opposite side is root 2 over 2. And then the adjacent side was root 2 over 2 as well. So we don't have to do any like crazy like multiply by the reciprocal here, because you're taking a number and you're dividing it by the same number. So anything divided by itself is just 1. So tangent of 45 degrees would be just 1. And again, it doesn't matter how big, what the side lengths are of these triangles, these trig ratios of these angles are going to simplify the same exact way regardless of size, because all these 45, 45, 90 triangles are proportional. So like anytime you're asked for cosine of 45, the answer will always be root 2 over 2. Or anytime you're asked for tangent of 45, it'll always be 1. Okay, so because we have these like consistent like answers every single time, it makes sense to kind of create a table for it. So here's the table. It has sine, cosine, tangent of 30, 60, and 45 degree angles. Those are all the angles in a special right triangle besides the 90, but we don't use like sine, cosine, and tangent for that. So save this table, keep it to reference, so you don't have to do all the work that we just did for these notes every single time. You can kind of back it up and know where it came from. but moving forward, you can kind of just reference this table to help you with a lot of the problems.